2 raised to 2k times k factorial times p plus 1, p plus 2, p plus k minus 1, all the way up to p plus k. We let A naught be given by 1 over 2 raised to 2p times gamma of p plus 1. Are you guys able to recall the relation between the gamma function and the factorial function? Some?
Kindly remind us.
Yes, Paul?
No.
Do you guys go through the gamma function in third year?
Yes.
Okay. Then that means we have to do... Okay, let's write this, then we pause, do a quick recap on the gamma function before we proceed. So if A naught is 1 over 2 raised to power 2p times gamma of plus 1, the relation between gamma and the factorial is gamma of something plus 1 is equal to that particular thing factorial. So gamma of p plus 1 is equal to p factorial. Let's insert this in the formula, then we pause, go to gamma function, and then we'll proceed. So this implies our s sub 2k will be given by minus 1 raised to power k divided by k factorial. We have 2 to the 2k times k factorial times, we have p plus 1, p plus 2, going all the way to p plus k minus 1. We have p plus k times, we insert our A naught. Our A naught is 1 divided by p times factorial. Let's pause and then go to the gamma function. We'll come back to that. Gamma function. Gamma function of x is given by the integral running from 0 to infinity, e raised to minus t, t raised to x minus 1 dt. Gamma function is defined by gamma of x is the integral from 0 to infinity e minus t 2 to power x minus 1 dt for x greater than 0. So that's to tell you gamma of 1. If gamma of x is the integral from 0 to infinity e minus t 2 to power x minus 1, then gamma of 1 is the integral from 0 to infinity e to minus t. In place of x, you substitute with 1, t raised to 1 minus 1 dt. 1 minus 1 is 0. So this is this antiderivative a minus t, t raised to 0, but t raised to 0 is 1. So this is equal to, we integrate between 0 and infinity, e minus t dt. You integrate e raised to some function, you differentiate the particular function at then you divide to To integrate e raised to f of t, it's the function itself e raised to f of t divided by f prime of t. In this case, our f of t is negative t. So you differentiate minus t with respect to t, you get minus 1. So the antiderivative e minus t dt is e raised to minus t divided by negative 1. We are evaluating this between 0 and infinity. This is the same thing as negative e raised to minus t. We evaluate this between 0 and infinity. We plug in the limits, starting with the upper limit. This is equal to minus e raised to minus infinity, minus in brackets, we subtract the lower limit, minus e raised to minus 0. What is e raised to negative infinity? E raised to minus infinity, Cheryl? Calvin?
0.
E raised to minus infinity is 0, minus e raised to 0 is 1. 0 minus minus 1 gives you positive 1. So this is one of the useful properties of the gamma function. We have gamma of 1 equal to 1. Next, let's investigate gamma of x plus 1. Gamma of x plus 1 is given to be equal to x times gamma of x. So we prove this result. Gamma of x plus 1. From definition of the gamma function, gamma of x is the antiderivative 0 to infinity e minus t raised to x minus 1. But in this case, we are having gamma of x plus 1. So in place of x, is someone just trying to join a meeting or there's a concern? We'd rather just unmute and speak up. So here we'll have x plus 1 minus 1 dt. This is equal to 0 to infinity e to minus t raised to x plus 1 minus 1 gives us t raised to power x dt. This is an integral of the form u dv, and the formula is uv minus the integral v du. So we have to let some function be equal to u in this case. Choose your u such that you can easily differentiate it, and your dv such that it's easy to integrate. So if our u is equal to t power x, what's our du? When you differentiate t raised to power x, what do you get? What is the derivative of t raised to power x?
xt to the x minus 1.
We pre-multiply by the power, which is x, t raised to decrease the power by 1, so t raised to x minus 1. V is e minus, dv is e minus t. Okay, these are dt here. Our v is minus e raised to minus t. The formula is uv minus, we integrate v du. Our u is t to power x, v is e minus t. So our uv will be minus e minus t times t raised to power x. Evaluate this between 0 and infinity. Minus, we integrate v du minus e minus t. Du is x, t to the x minus 1 dt. If we evaluate minus e minus t power x between 0 and infinity, we'll have minus e minus infinity, infinity, minus e raised to minus 0 times 0 raised to power x. Factor out the negative, we have plus, we integrate between 0 and infinity, x e to minus t, t to x minus 1 dt. E raised to minus infinity is 0, so you'll have 0 times something minus 0 times something. The whole of this becomes 0. So this is 0 plus, factor out x as a constant, integrate between 0 and infinity, e to minus t, t to the x minus 1 dt. This is just equal to x, 0 to infinity, e minus t, t to the x minus 1 dt. But what is the integral from 0 to infinity e minus t to t raised to x minus 1 dt? We started by defining the gamma function, gamma of x. What is this quantity from here to here?
Gamma of x.
This is gamma of x. So we have an x outside times gamma of x. On the left, we are trying to evaluate gamma of x plus 1. So in other words, we have gamma of x plus 1 is equal to x times gamma of x. So whenever you have gamma of some quantity, say a plus 1, it's the same thing as a factored outside times gamma of a. If you have, say, gamma of a plus b, then plus 1 here, then this is factor out the a plus b times gamma of a plus b, and so on. We can now move to the relation between the gamma function and the factorial function by investigating what gamma of n plus 1 equals. Gamma of n plus 1 is equal to n factorial. Let's verify this result. We need to show that gamma of n plus 1 is equal to n factorial, but from definition we have gamma of n plus 1. Using our previous result, what is this equal to?
N gamma of n.
Gamma of n. So gamma of n plus 1 is equal to n gamma of n, but we can obtain an expression for gamma of n, then plug it here. We use the same definition. Gamma of n plus 1 is equal to n gamma of n. What is gamma of n? Notice that if I say n is equal to n minus 1 plus 1, if I subtract 1 and then I add 1, you are adding a clever 0, minus 1 plus 1. You'll still have the same thing, right? So you can express your gamma of n as gamma of n minus 1, then plus 1. But we know that gamma of something plus 1 is equal to that something factored out, then gamma of that particular quantity. So this will be n minus 1 times gamma of n minus 1. Let's use this result. We had that gamma of n plus 1 is equal to n times gamma of n, but now we are having gamma of n is n minus 1 times gamma of n minus 1. Let's obtain an expression for gamma of n minus 1 as well. Gamma of n minus 1. If I subtract 1 from n minus 1 and then add 1, I'll still have the same thing. So this is equal to gamma of n minus 1 minus 1 plus 1. This is gamma of n minus 1 minus 1 plus 1. But minus 1 is minus 2. So this is equal to gamma of n minus 2 plus 1. Again, when you have gamma of something plus 1, it's equal to, you factor out then. So in this case, gamma of n minus 2 plus 1 is equal to n minus 2 times gamma of n minus 2. So we are finding that gamma of n minus 1 is given as n minus 2 times gamma of n minus 2. We can go ahead, obtain an expression for n minus 3, then we can stop there. I mean n minus 2. Gamma of n minus 2 is the same thing as gamma of n minus 2. If I subtract 1, then add 1, I'll have the same thing. This is gamma of n minus 3 plus 1. But gamma of something plus 1 is, factor out the n minus 3, then gamma of n minus 3. So in other words, we are having gamma of n plus 1 equals to n times n minus 1 times n minus 2 times n minus 3 times all the way up to, this will proceed all the way up to gamma of 1. But we just proved that gamma of 1 is equal to 1. So using the result, we have gamma of n plus 1 is equal to n times n minus 1 times n minus 2 times n minus 3 times all the way up to 3 times 2 times 1. But what is n times n minus 1 times n minus 2 all the way up to 3 to 1?
N factorial.
Yeah, it's equal to n factorial. So this is a very important relation. Gamma of n plus 1 is equal to n factorial. You can use them interchangeably. So if you have n factorial, you can express the n factorial as gamma of n plus 1. So assuming you have gamma of, let's assume you have n plus, let's say, m factorial. We can express this in terms of the gamma function as gamma of n plus m plus 1. Or we need to take a remark. When is the gamma function defined? Gamma of x plus 1 the argument of the gamma function must be greater than 0 when x plus 1 is greater than 0, or this is the same thing as x is greater than negative 1. So we need that the quantity inside the gamma symbol should be greater than 0. From here, I think we can now proceed. We can now go back to our s sub 2k. It was given as minus 1 power k 2 raised to 2k, k factorial, p plus 1, p plus 2, all the way up to p plus k minus 1, p plus k, times, we had let our a naught be equal to 2 raised to power p times gamma of p plus 1, but we know that gamma of p plus 1 is equal to p factorial. So we have this times 1 over 2 raised to p times p factorial. Screen is misbehaving. So let's collect. We are having 2 raised to 2k, then we have some 2 raised to power p. The screen. Like this.
Was it 2 raised to p or 2 raised to 2p?
Sorry?
You had written 2 raised to power 2p.
It's 2 raised to power p.
Okay.
Can make that correction. Let a naught be equal to 1 over 2 raised to power p times gamma of p plus 1. This is minus 1 raised to power k over 2 raised to 2k. We can bring the 2 raised to power p here. We have k factorial. We have p plus 1, p plus 2, all the way to p plus k. Then we have a p factorial here. 2 raised to power 2k, 2 raised to power p. The base is the same. We can combine the powers. So this is minus 1 raised to power k divided by 2 raised to 2k plus p times k factorial. Then we have p plus 1, p plus 2, p plus k, p factorial. I want us to look at the p plus 1, p plus 2, all the way up to p plus k term. Screen is not doing justice. I want us to look at this term, p plus 1, p plus 2, all the way up to p plus k. If we read this backwards, if we start with p plus k, maybe I can just rearrange it. P plus k, the second last is p plus k minus 1, all the way up to p plus 2, then p plus 1. Let's rearrange this term. We start with p plus k, then go all the way up to p plus 1. So we are having a sub 2k equals minus 1 raised to power k divided by 2 raised to 2k plus p times k factorial times, if we start with p plus k, then we have a p plus k minus 1 all the way up to p plus 2, p plus 1. We only dealt with this. We started with p plus k backwards to p plus 1. There is a p factorial here, so we have the p factorial here. Looking at p plus k all the way up to p factorial, looking at this term, what is it equal to? You have p plus k, decrease it by 1, go all the way up to p plus 2, p plus 1, then times p factorial. What is it equal to? How can we express this in terms of the factorial function?
P plus K factorial.
Yeah, this is equal to p plus k factorial. So we replace that with p plus k factorial. And our s sub 2k becomes minus 1 power k divided by 2 raised to 2k plus p times k factorial times k factorial times p plus k factorial. There is a way we can express p plus k factorial in terms of the gamma function. We just went through that. P plus k factorial is equal to gamma of what function?
P plus K plus 1.
Gamma of p plus k plus 1. So we substitute p plus k factorial with gamma of p plus k plus 1. And we have a sub 2k equals minus 1 power k divided by 2 to the 2k plus p times k factorial times gamma of p plus k plus 1. We were obtaining a series solution to the basis differential equation, and we assumed that y of x is the summation from k is 0 to infinity s sub k x to the k plus s. But on solving the recurrence relation, we noticed that we'll only have even values. So we do not have an s sub k, but instead we have an s sub 2k. So our y of x will be equal to summation k running from 0 to infinity a sub 2k x to the k plus s. No, so in place of k, we have 2k. A sub 2k x to the 2k plus s. But we are obtaining an expression for the solution corresponding to s equals p. So we also substitute s with p. And our y of x is the summation from k is 0 to infinity s sub 2k x to the 2k plus ss, we substitute with p, so we have x to the 2k plus p. So our y of x is the summation from k is 0 to infinity s sub 2k x to the 2k plus p, but we just obtain an expression for s sub 2k. So let's use that expression in our formula. And we have our y of x is the sum from k is 0 to infinity. What's the formula for s sub 2k? Minus 1 raised to power k divide by 2 raised to 2k plus p times k factorial gamma of k plus p plus 1. That is s sub 2k. We are multiplying this with x raised to the 2k plus p. We can do a bit of rearranging in the denominator. We start with k factorial gamma of k plus p plus 1, then write our 2 to the 2k plus p. So this is the summation from k is 0 to infinity minus 1 raised to power k divided by, let's start with k factorial, gamma of k plus p plus 1, then times 2 raised to 2k plus p. This is multiplied with x raised to the 2k plus p. The screen is... Let me just rewrite that step because my screen is behaved. Our y of x is the summation k is 0 to infinity minus 1 to the k over k factorial gamma of k plus p plus 1, 2 to the 2k plus p. This is multiplied with x to the 2k plus p. If I have a raised to power x divided by b raised to power x, we can write this as a divided by b, the whole thing raised to power x, right?
Yes.
Batman. But it was holiday. We were supposed to be sleeping up to 10 a.m. Wasn't that the agreement?
Watch.
Huh? You want to watch? So we said 11 a.m. You said you'll watch at 11. Mm-mm. So we are having an x raised to the 2k plus p divided by 2 raised to 2k plus p. We can say this is x divided by 2 raised to 2k plus p. So our y of x, our solution y of x becomes y of x equals sum from k is 0 to infinity minus 1 raised to power k divided by k factorial gamma of k plus p plus 1 times x over 2 raised to 2k plus p. This is the solution corresponding to the index s is equal to p. So the index s equals minus p. For s equals minus p. So the whole of this expression is what is known as jp of x. So jp of x is the summation from k is 0 to infinity minus 1 power k divided by k factorial gamma of k plus p plus 1 times x over 2 raised to 2k minus p. The solution corresponding to s equals minus p. We replace p with minus p. We substitute p with minus p in the above formula. And it means we will have, so we substitute p with minus p in the formula for jp. So if we are replacing p with minus p, then we have a j minus p of x equals the summation from k is 0 to infinity minus 1 power k over k factorial gamma of k plus p, but p is minus p, so k minus p plus 1 times x over 2 raised to the 2k minus p. But when looking at the gamma function, we noticed that the argument of the gamma function must be positive. So if j minus p is the sum from k is 0 to infinity minus 1 power k over k factorial gamma of k minus p plus 1 times x over 2 raised to 2k minus p, the argument of the gamma function must be greater than 0. But in this case, we are having some k minus p plus 1. K is running from 0 to infinity. What happens to the case when k is less than p? If k is less than p or p is greater than k, then k minus p will be negative plus 1. You still have a negative, but we require that the argument of the gamma function should be greater than 0. So to avoid this case, we have to to avoid the case, to avoid a case where we have to evaluate gamma of some negative quantity, we have to work on the index k, because for the case where k is less than p, then we'll have the argument being negative, and we don't want that to be the case. So we have to specify that k should be less or equal to p. If k is equal to p, then if k is equal to p, k should be greater or equal to p. If k is equal to p, then we have p minus p is 0 plus 1. Gamma of 1 is 1, as we know. If it's greater than p, then something greater than p, it will take care of that. So we'll not have a negative argument. So k should be greater or equal to p. Or in other words, we're just saying that k should run from p to infinity and not 0. So for j minus p of x, we'll have that this should run from k equals p to infinity minus 1 raised to power k divided by k factorial gamma of k minus p plus 1 times x over 2 raised to 2k minus p. So you have j minus p of x is the summation from k equals p to infinity minus 1 power k, k factorial, gamma of k minus p plus 1, x over 2 raised to 2k minus p. So summing from k equals p to infinity, j minus p of x is, my screen keeps on, k is p to infinity minus 1 power k, k factorial, gamma of k plus p, k minus p plus 1, x over 2 to the 2k minus p. If we specify that k should run from p all the way to infinity, then we successfully take care of the case where the argument of the gamma function, we make sure. Do you know you're distracting me, Batman? So if we specify that k should run from p to infinity, then we are taking care of gamma of k minus p plus 1. But again, we want a case where k is just running from 0 to infinity for the Bessel function. So we do something called reindexing, just like we did yesterday, by setting the k minus p equal to some other index. If we set k minus p equals to some index, say m. Then you want to sum over m. You'll need, if you set k minus p equals m, then if you want to deduce an expression for k in terms of m, making k the subject, you have m plus p. So we can replace k with m plus p in our formula, but we are summing over m, so we need, you please help me with this? Can remove one of the sockets.